Okay, so good morning. So my name is Yi. So I'm from UC Merced. So actually, I'm just a presenter. So my friend Zhongfa and his team is actually the participant in this challenge. And I'm glad they achieved a good performance, but unfortunately, they cannot come because of the visa issues. So later when I say our work or we did something, so actually it's they did, so their work. And so before I start, I want to thank you to the organizers for such a great challenge, and it's very good for our researchers in this field. So this is the overview of my presentation is, so first we will describe the literature a little bit, and then I will propose the network of the iResNet. So basically it's an iterative residual prediction network for stereo matching. So we call it ResNet. It's not because we use ResNet 101 or 50. So it's because it's a residual prediction network. So basically, we predict initial disparity first, and then we do residual to it. So hopefully, it can get better and better. And the most important thing of our approach is we use a multi-scale feature constancy. So there are two types of the feature constancy. So one is a correlation layer. The other is a reconstruction error. So the reconstruction error we're doing here is not image-based. We're doing on feature-based. So hopefully it can be more robust. And the third thing is our training strategy. So it's a two-stage training and a two-stage fine-tuning. So basically there are 4 stages of training here. So the previous work, so the first one is, of course, the Disparity C, so which is proposed in the CVPR 2016 work, the SynFlowNet. So it's a very good, impressive work to regress disparity end-to-end, and it's fast, and also those following work of FlowNet, FlowNet 2, and all is very good. And the input of the network is the two images, so it's a stereo pair, so left and right, and then go through an encoder and do a correlation layer, and then following the decoder to recover the high-resolution disparity map. So later, so there is another work called CRL. It's a cascade residual learning. They just do one forward with the Disparity C network. So basically, they adopted Disparity C network first to estimate the initial disparity, and then they do another network called DispaResNet. So similar to FlowNet 2. So basically, they give the image I left and I right and the reconstructed I left, and the error map and the disparity maps, all the input to the second network. So hopefully they want the network to learn from those information. So because those are confidence estimate. So hopefully they can learn better residuals. So after they learn the residuals, they just summarize with the previous initial disparity estimation. So add them together and to get to the final estimation. So that is a CRL approach. So our work called iResNet, so basically is inspired by the 2 previous work, so the Disparity C and the CRL. So we explored multi-scale feature constancy here. So the multi-scale here is because we have multiple data sets in this challenge, and for the data set, the data distribution, the disparity distribution is not the same. So by using multi-scale, we can achieve a more robust result. And so our network have 4 stages. So the first stage is a multi-scale feature shared features. So maybe you cannot see it, so it's very below. So it's the first stage. So it's for shared features. So those are Siamese networks, so they are shared parameters. And then go through the middle is an initial disparity estimation, so which is the Disparity C network exactly, so no modifications. And then the third stage is a disparity refinement, which is actually the most improvement we can get from there. So it's a shallow encoder-decoder network, but if you consider we use the shared features before, so it's actually not shallow, it's very deep. And in the end, we get the final disparity map. And later I will illustrate that to each stage in detail. And there are 2 multi-scales here. One is in the correlation layer, and the other is when you do the feature construction. So there are 2 multi-scales there. And for reference similarity, so for the first stage of the feature extraction and the initial disparity, we call it the initial disparity estimation subnetwork, so the DESNet. And the later network is the disparity refinement subnetwork. We call it the DRSNet. So for the feature constancy, so it basically means we want to compute the correspondence of the 2 pixels in the feature space. So not in the color space, so it's in the feature space. So like the stereo matching. So there are 2 types we consider here. So one is a correlation layer. So correlation is they want to establish at each possible disparity location. So for example, if we want to find the matching point in the color space, so the point will be on the epipolar line, and we're just searching the 1D domain. And in the feature space, so it also should lie in the local neighborhood. So we can set this max displacement. So in our experiment, we set it to like 50 pixels. So that correlation layer is conducted after the Conv2 layer. So basically, the image resolution is already reduced by 4 times. So that means the 50 pixels in the feature space recovered to 20 pixels in the original image space, so which can cover all the large displacement in the data set. So then when we do the searching, so if we can have a larger value of correlation, it basically usually means we already find the correct disparity for the correspondence. And the second type constancy we consider here is called the reconstruction error. So before in the CRL work, they are doing on the image space. So given the disparity and the 2 images, so if the disparity is correct, so we can fully recover the first image from the second image. But if we using the disparity, doing the reconstruction, if the error is large, that usually means that disparity is incorrect. That means we cannot find the correct matching. So that's a basic 2 loss functions were used to doing the feature constancy. And for the multi-scale here, so what we propose a modification is before in the Disparity framework, if we see the diagram, so it's Conv1A, Conv2A, and they directly do the correlation. Okay, so that means so that 2 convolutions are straight 2. So the resolution of the image is reduced by 4 times. So which means the receptive field is like 15. But that is a little bit small, so we want to make it larger and to cover like a large movement of vehicles. So we propose a very small encoder-decoder network here. So we just, after the Conv2A, we add another convolution layer and a deconvolution layer. And we add a skip connection to that. So in this case, we're doing a multi-scale features, and the receptive field can be increased to 47. That is the first advantage. So the receptive field is larger. And the second advantage is, so here we're not only using the Conv2 features anymore. We're using the Conv2, Conv3, and the deconvolution, so upsampled features as well. So we use multi-scale features. So that should be better than only use Conv2 features. And the third advantage is we try different feature pooling method to see if our method is better. And there are 2 widely used method. One is ASPP, the other is a 4P, so which is a per pixel pyramid pooling method. So the per pixel pyramid pooling method, they're just doing like inception module, like the bottleneck layer. So like 1 by 11, 11 by 1, and 5 by 5. So those small kernels inside the module, and hopefully they can learn like multi-scale feature maps. And for the ASPP, the Austria Spatial Pyramid Pooling, so basically they use dilated convolutions with different dilated factors, so 2, 4, 6, to achieve different multi-scale features. And we try both in our network. And as we can show in these tables, the table, it is tested on the SynFlow validation set, which is the 4,000 images of the flying thing 3D data set. So for the single scale, we get 1.26, and using ASPP and 4P, we can get 1.17 or something. And the multi-scale is we can get like a 1 point. So it's a very large improvement. And the second type of constancy we considered are the reconstruction error. So the reconstruction error we do is in the feature space. So in the feature space, so we're like robust to noise and all those like Gaussian noise and the luminance changes, gamma changes, all those brightness changes. And I think there were many works this year and using feature reconstruction to do the optical flow disparity work. And the second good thing is, I will show later in the diagram, but first here is our network is more compact. So if we see in the CRL work, so you use one DispNet to do the initial disparity estimation and using the second network to do the residual network. But the input to the second network is still images. So they still need a quite deep encoder to get the features. But actually here, we do not train another encoder. We just use the features from the previous encoder to directly do the decoder. So our network is more compact, so which leads to a robust performance. So if we consider the model parameters here, so we're only 44 million parameters compared to like 80 million in CRL, so almost half of the parameters. And for the multi-scale effect, so multi-scale has a little bit edge over the single-scale scenario. So by sharing the features, so we don't need to extract the features anymore. So if you can see here, so if we only see the disparity refinement network, it's only a 3-layer encoder-decoder network. It's pretty shallow. But if we consider all the features skip connected to the later one, it's pretty deep. So it's still like a 6 or 7 layer of the network. So we don't need to extract features from the input images. And And the third thing we do is the iterative residual prediction, so which is in the name, so iResNet. So basically, so we give the input images to the DESNet and then go to the DRSNet. So because our DRSNet is pretty shallow, so we can just do a bunch of them. So again and again to improve the performance. And the table here shows, so if we add one DRSNet, it achieves like a much better performance, and the second and third, and until the third, the performance kind of already saturated. So we don't add any more. So we just use one DESNet and 3 DRSNet to do the whole model. And in the final is our like a training strategy. So the first is a 2-stage training strategy. So on the left, we first use MSRA initialization strategy to train the model, just as DispNet C do. And after that, we use that model to train it again. So because we think that model will be a better initialization. So we train it again following the same recipe, and that is our 2-stage training strategy. And during the 2-stage random fine-tuning, basically is, so model should be performed well, so no matter which data set it tested on. So no matter on the pre-trained data set or in the later other data set we want to test on. So there are several strategies to do that. So one is, so if we pre-train the model and fine-tune it on that data set, on data set A, on data set B, on data set C, so just fine-tune it on each data set. But the problem with that approach is you may get a better performance on A, but like a worse performance on other data sets. So how do we overcome that? So we just random fine-tuning that by using a data switch layer. So basically we use the 4 data set together and during each like a mini batch. So we only extract images from one data set, but do iterative over them. So in this case, we can learn different like distributions from different data set, and it proves to be very effective. And here's the result. So although I think we didn't achieve like a first place in any of the data set, but in overall, we achieved good performance. And I think that's because the 3 things we proposed here to make sure the robustness of our approach. So the first thing is iterative residual prediction. The second is a multi-scale feature constancy. And the third is a 2-stage random fine-tuning. And the code is already released here, and it's in Cafe. And I think the reason why the author asked me to do the presentation is because I reproduced their method with TensorFlow before, so I'm kind of familiar with the work. So hopefully I will also release my code to further let the method widely adopted by you. And in the end, if you have any questions, you can ask him or you can ask me, so hopefully I can answer them. And here is a reference to all the previous work. Yep. Thank you.
All right, thank you for the perfect timing. We have time for questions. Please walk up to the microphone.
Yeah, I think it's pretty forward.
Well, I have a question if no one else has a question. So my question is, the point of the robust challenge is to be robust to a wide variety of data sets.
Yep.
But in some sense, you now trained on the wide, well, narrow 3 data sets that we had in this challenge. So how well would you then expect this to generalize to something you haven't trained on at all?
Okay, that's a good question, but I think as long as the distribution of the other data set is similar to this one, it should perform well, because we already added so many like constant assumption like prior into this framework. But if the distribution is totally different, like the displacement very small or very large, then I don't think it will generalize well. That is an open question now. Yeah, thank you.
Any other questions? All right, if not, then let's thank the speaker again.
Yep.